and those are non-polar. So I can adjust this capacitor in any way I want or in any orientation. And then on the right here, the furthermost here, this component is an electrolytic capacitor, or sometimes called a foil capacitor as well. And what makes this useful is that they are polarized, meaning on the one side, and I can't quite make sure which one is positive, is the positive pin, and the other one is the negative pin, and you will always have to connect the positive to the negative pin. Now you might be asking, okay, but if I have capacitors that are non-polarized and I can just use any orientation I want, why not just use them? Why use electrolytic polarized components? A lot of reasons. Usually the polarized electrolytic components are cheaper and come at a very higher rating and also higher values. So if you are looking for a capacitor with maybe a 1 solid 1 farad capacitor, it is easier to find a electrolytic capacitor that can do that for you than have a non-polarized capacitor, because usually they come in micro, pico, or nano variants. But the polarized capacitor in a general sense are just bigger and most of the time cheaper as well. So these are all trade-offs that you will need to do in circuit design. You might find components that are really expensive and would work really well for your specific circuit, but then if they're not available or too expensive, you can't use them. And we have some resistors. Of conductive and insulating layers. So what does that mean? Well, generally, when I speak of something being a sandwich, it means that I have 2 layers of the same thing with another material between them. So I would have a laminated sandwich. So I might have on both sides conductive material with a non-conductive material in between. So whenever I say something is sandwiched between them, it means that I have 2 materials being separated by something else. Now also with PCBs, just diving into a little bit into the terminology, I could have a single-sided PCB. When I say single-sided, that means that I have conductive material like copper only on the one side. So I would have copper and then my substrate, which is the non-conductive backing material. And that I call a single-sided PCB. I can then move on to having a double-sided PCB, meaning that I will have a layer of copper, my substrate, and then another layer of copper on the other side. Meaning on both sides, I would have copper, and I can connect components on the other sides as well. So single-sided, double-sided, but then we can also have 3-layer, 4 layers, 5 layers, 6 layers. And that means that counts the amount of conductive layers. So single-sided would be 1 layer, double-sided, 2 layers. If I have 3 triple-sided, you would have 3 layers. So in terms of that, I would have conductive material, substrate, conductive material, substrate, and conductive material. 3 layers. And it can almost be an infinite amount of layers. Now, why would I have more than just 2 layers? Because surely I can't put components between layers. Well, more or less, that would be the right idea that you have. But there's another reason you might have more layers. And it's something we can have a look at when we have our components, is that when you have your components, let me just have a look. They all have their own unique path or connection path in that layer. So I have my component, my 2 resistors, and they are connected with a certain physical path. Now, my 2 tracks on the same layer cannot cross because they are both made of copper. If they cross, they make an electrical connection, and then that track is in fact connected. So if I have then 2 components, they will each have their own unique tracks. But what if I have now thousands of components? How do I create unique tracks between those components without them connecting? I'll show you a I'll show you an example of a very complex circuit board, if I can find it in the break. So if I have thousands of components, the difficulty becomes in connecting those components. Because I can make my board as big as I want, but if I have 100,000 of very small components, it's not that easy to connect them. So then I add in layers so that I can have on my 1 layer a component. It is then connected to a 3rd or a 4th layer, like in this direction. And then it runs with the track to another direction and then is connected to another component through these layers. So you can think of this as in terms of a 3-dimensional connection. Whereas I have 1 layer, everything is 2-dimensional because everything is connected in this connection. But if I add more layers, it becomes easier to connect my components. But we'll have a look at this once we start creating our components, because it does become really difficult in connecting your components. But like I said, if this is a little bit confusing, don't worry about it. Once we start designing our own PCBs, you'll come to realize like, oh yeah, this is what he was talking about. This is why it becomes so difficult. Right, no, I'm not going to show that for now. And just as an interesting fact, I think your motherboard of your computer. Let me just, before I start lying to you, I just want to figure this out. How many layers? Okay, so I just quickly Googled how many layers does a motherboard of a computer have? Sorry for the delay. And it says it can have 6 up to 14 layers. So the motherboard of the computer that you're looking at me at, hopefully, could have up to 14 layers. And it's still like that thick. So sandwiched in between your motherboard, if you ever look what a motherboard looks like, you might have 14 layers. So you would have a layer of copper or whatever conductor material, substrate copper, substrate copper, substrate copper, substrate copper, repeated 14 times. And like I said, we do this just to ensure that our components are easier to connect. Because I just want to show you another picture. Yes. Sorry, I realize this is not great. You have something called a ball grid array. not really a side topic. Most of the microchips or the processing chips that your computer uses, if it's Intel or AMD or whatever, it doesn't matter. But they all have these flat chips, and at the back of them, they will either have balls, like lots of little balls, or lots of little pins. And they look a lot like this. I'm showing my screen. And this on the right is what we call a ball grid array. Up here, you will see that it is connected to this. So all of these connections, just trying to find, if I look at this, all of these are unique electrical connections. So if you have a microcontroller or a processor in this case, all of those connections connect to something internally, and you might need access to those on your PCB. So you can imagine if I have all of these connections, all of these have to be unique connections. None of those ball grid array wires or connections can cross, because then you cause a short. So if I have something this small with 96 connections at the back, for instance, it becomes very hard to connect them. So that is why we add in multiple layers. So I can stick the ball grid on one side and then connect through my different layers everything on that chip, which becomes really difficult once you enter things like that. But don't worry about it. We'll have a look at an example, I guess, how we can be able to do that. But EagleCAD does make it a little bit easier and makes your life a little bit easier, because it does have a tool that would like automatically connect it and automatically tell you how many layers you would initially need. So back to the presentation. Let me just do this. And also PCBs mechanically support electric components using conductive pads in the shape designed to accept the component's terminals. Also, they electrically connect them using traces or tracks. And components are generally soldered onto PCBs to both electrically connect them and physically fasten them to the component itself, to the board itself. Now we're going to talk about the process called soldering. Let me just take a sip of water. Just keep an eye on the time. Right, so soldering is a process which two or more items are joined together by melting and putting a filler metal, typically solder, into the joint. The filler metal having a lower melting temperature than the adjoining metal. Soldering can be made by hand, like we have in this picture at the top. You have something we call the soldering iron, and then the solder. I touch the iron to the component I want to attach another component to, and then I also touch the soldering wire to it to melt the solder. The solder then hardens and then physically connects the two components. Now, this is a manual soldering, and on the right side, you have a soldering machine, or commonly sort of use a pick and place machine that would pick and place the components like not at random, but it will use and connect them. Now, all right, I might have a I might also in one of these lectures just have a quick look at how I solder different elements. It might be also interesting. So I'll try and work in on a different class. Sorry, I just have to think about this. Right, so if we have our printed circuit board or our Vera board, for instance, then we will need to connect our components to the circuit. And that is quite commonly done with soldering, not soldering, soldering. So the solder, like I said, you have a soldering iron, you touch, it becomes very, very warm, and it melts solder, and that connects the components together. Let me just, I think I might be able to have like a short demonstration of what I do if I can get my other camera working, but we'll check that out. Oh, yes, definitely. So just to have another idea, I'm just going to take away my. So this is my circuit board, and you can see. So this obviously is the circuits connected, or the components connected on the one side and the back side of my circuit board. So obviously this is a single layer PCB because I have my substrate, the non-conductive material, and on the back side, now this is copper, but this copper is coated in another material that makes it non-conductive, so that's why it doesn't look like copper, because it just so that it does not react to the atmosphere. So I stuck my components, that's a resistor, through there. On the other side, I then use a soldering iron to solder them to this component. And as you see, you might be able, I might get a camera just to have a better look at this. You can see that it is not that great. I keep this around just to remind myself that soldering is very hard, and it's something you will need practice to get right, or to get right consistently. But I think I can. Right, so this is like I said, a circuit board that I made a very long time ago, which I designed, chose the components, and then soldered at the back. And I think 15 years on, it still works. Just to give an idea, the circuit, I think it was during my studies, we had to use a microcontroller. This big thing here is a certain microcontroller. And we wanted to have what we call a development board, so that we can use and connect this microcontroller to a programmer, and then also to have it connect to other components. So we created a board. We have some lights we can connect it to with resistors, and also the screw connectors, so we can insert wires and screw them closed. We've got a CMOS battery, which I think powers a real-time clock, and all of these elements so that I can use this little board. And hopefully, by the end of this course, you should be able to do something relatively simpler, just hopefully better than what I managed to do. Okay, we're coming up to the end of this specific session. Yes, so we will have, I think, what is it, a break of about 2 hours or so. Let me just check, make sure that I'm not lying to you. Right, yes. So we are, let me just share my screen so you're looking at what I'm looking at as well. So this is the schedule. Now this class is now just finished, and it should be 5:30. And then we start again at 7. So we have about an hour and a half of a little break. Then I'll continue the lecture on that time. Now, as well, I am going to be leaving this session or this Teams meeting, but I will be rejoining at 7 o'clock. And you can do all the same. So you can leave the session, do something else, and just rejoin the session later. If anything happens and you cannot rejoin the session, send me an email or have somebody else post in the chat. And yeah, I'm guessing if you have something to eat, you don't have it, have a little bit of time to relax. And then after this, we will hopefully finish with the theory part and then hopefully start with some practical stuff, which is a little bit more interesting. So, okay, I'm just going to put it in the chat so that everybody are aware. We're having a break in between sessions.